To begin with, let me say this is joint work with Nikolai Yorgov, Oleg Lisovy, and it is inspired by some remarkable paper of these two authors together with Gamayan. Oh, sorry. I need to get some reading glasses. Where they observed that there is a relation between conformal blocks at c equals to 1 in the 4-punctured sphere case and the tau function for penalty v6. That's a remarkable result for sure, which was, I think, for many quite unexpected. And the following, say, sort of is emerging from some attempt to understand why this is so and how to generalize. And right, so let me start. And this basically gives away the punchline by introducing the very classical Riemann-Hilbert problem. And the point is going to be C equals 1 conformal blocks can be used to give a, if you wish, bosonic solution to this problem, as opposed to the well-known solutions that exist due to Kyoto School, for example, Jimbo, Miwa, Sato. It is not one using free fermions, but using C equals 1 Virasoro representation theory. And the relation between the two ways of solving it, of course, should have very interesting consequences that I hope to comment on a little later. So we shall consider n-punctured sphere. And the fundamental group, pi1 of the n-punctured sphere, of course it has generators. I will denote how, well, gamma 1 to gamma n. So if this is, say, z1, zn, I can think of them, and maybe I choose a base point, as I will often do, y0, then I can think of these generators being represented by closed contours starting at y0 and encircling these punctures once. And there's, of course, just one relation, gamma 1, gamma 2, and so on. Taking the product of all of them is to be trivial. Now we're interested in representations from pi1 into P SL to C, which will be described by a collection of matrices representing the generators M1 to Mn, well, satisfying basically the corresponding relation now. That is probably obvious, needs not to be written. And what we will assume is that the MKs are diagonalizable and have eigenvalues which we will keep fixed once and for all, e to the 2 pi I, what's the notation, mk. PSL2C, what it is? Yeah. So it is SL2C modulo the plus or minus identity.
You mean group or algebra? So
Group.
And what for you need this identity?
Well, that represents the relation in the fundamental group.
So plus minus, you include.
Okay, yes, of course I should. I'm a little sloppy here about these issues. Of course, the interpretation of this relation has to take into account the p properly, etc. But okay, let me not spend too much time on this. So, Riemann-Hilbert problem is then to find matrix valued function capital Y of small y, which is multi-valued analytic on C0n. Often it is also required that it is invertible, such that the analytic continuation of this function that I'm going to denote by gamma k dot y, so that's the result of analytic continuation of this function along the contour gamma, is represented by right multiplication by this corresponding matrix. Okay.
So this y is equal to C value?
Yes, that is right. Yes, that is right. And what shall be useful is, okay, we're keeping fixed these parameters. We want to introduce a useful parameterization for the remaining degrees of freedom, which is contained in the choice of the matrices Mk. Parameterize Mk. Well, also I should say, of course, we're considering these collections of matrices modulo overall conjugation, which is the natural symmetry here in the problem. So in order to do this, I shall use Pan's decompositions, and I've prepared here sort of the description of the algorithm and the picture for saving a little bit of time. So, okay, first of all, replacing the punctures by little holes, one can think of the C0n as an n-hole sphere, and it's of course well known that by cutting along n-3 non-intersecting closed curves, we can decompose this into pairs of pans. Here, what is drawn is the case n equals to 4. We're going to do it in such a way that we're, say, decomposing into pairs of pans plus little cylinders. Well, that's what we can always do. That's not a big deal. And right, and if we now, so the algorithm, we want to associate to a collection of parameters which we assign basically to the boundary components of the spheres. So to each boundary component, we associate a parameter, say, sigma, and we're also assigned here, say, to the boundary components which are created by the cutting parameter sigma correspondingly. And we assign here to the little annuli some extra parameter which we call tau. So in this case, tau1. And out of these parameters sigma and the parameters tau, we want to produce the matrices Mk according to a certain algorithm. So this will give us a way to parameterize the matrices in terms of the collection of parameters sigma and tau. What I should immediately add is the sigmas here, if it is external boundary component that it is not produced by the cutting, then it is going to be identified with this parameter M1, which was giving the eigenvalues of the matrices we were keeping fixed once and for all. Good. Now, how does it work? We may now, in the Pan's decomposition, using the Pan's decomposition, we may decompose the contours gamma into arcs, which are, say, contained in each of the pairs of pans or annuli. So I did it here for the contour which surrounds the boundary component 2 prime. And okay, you see we go here, 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 then we go once round, and we go back in this way. And we see all we have the pieces are either arcs connecting boundary components of annuli, or the curves surrounding boundary components. And to these we associate matrices. So if this is arc running from boundary component I to j, we're associating this matrix, which is just built, which just depends on the variables associated to the respective boundary components in a rule which is perhaps almost obvious. To the annulus, we associate a diagonal matrix which contains these parameters tau. So here's the only place where parameters tau appear, by the way. And then there's the monodromy matrix itself, which is basically the elementary monodromy surrounding here this boundary component we would have when actually diagonalizing this, the monodromy. And this is given here by this formula. So this can be either external, then it is one parameter sigma, or then it is the m, or internal, then it is called sigma. All right, so let's give some algorithm. So at the end is we have
T and M are diagonal and F
is not. Yes, that is right.
And F differs from T by existence of O in a certain area.
So this is associated to annulus. This is for 3 whole square. Okay, so this makes mk a function of sigma and tau, and maybe m's if I want to separate, say, the internal to the external parameters. And okay, so that's what the parameterization that we want to use. And Nikita will have realized these parameters are guys he knows very well. Namely, these are the parameters that Nikita, Samson, and Alexei have used have put to very good use in applications to gauge theory and to integrable models. So NRS stands for Nikita, Samson, and Alexei. So more precisely, sigma is going to be up to some factor 2 pi proportional to I alpha, and these parameters tau are proportional to I beta plus f of alpha. Well, you will realize, so this means these are also Dabou coordinates, but not exactly those that were used in this paper. However, for many respects, they are as good as those which are used there.
Is this the shift which gets rid of the square roots?
Yeah, it gets rid of the square roots in particular, indeed. Right. Okay, next section is equals 1 conformal blocks. So a priori now it's for something completely different. I will briefly introduce the results and definitions about Virasoro algebra and representation theory of it that we are using. So Virasoro algebra is this infinite dimensional algebra with generators Ln and the well-known relation. And well, for the moment, maybe we can keep it in the background. And the representations we're going to consider are denoted VP, Verma modules generated from highest weight vectors P, which satisfy Ln P is 0 for n bigger than 0, Ln P, and that's the main notation we need to introduce, is Q squared over 4 plus P squared P if C equals 1 plus is parametrized in terms of parameter Q in this way. But we see in order to get C equals to 1, we have to set this Q equals to 0. And that's what we are going to do then for the rest of the talk. We want to introduce CVO, which stands for chiral vertex operator. Notation is going to be Vm P2 P1. What is this guy? This is a map from representation Vp1 to Vp2 such that it satisfies the commutation relation or the intertwining property Vp2 P1 M of Z equals commutator equals Z to the N Z dZ plus delta M N plus 1 and then the N P2 P1 of Z. I should have said that this guy is what will be denoted delta P. All right, so it is well, yes?
Delta M is just M squared?
It is just M squared here, yes. I could have written M squared, yes, sorry, it's just, okay. Anyway, you know. Good, and it is well known that this intertwining property defines this operator uniquely up to normalization. The choice of normalization factor does matter at some stage, but let me suppress this. So it is for some of the formulae that will, in the very end, appear, it does matter. However, it's maybe not the thing I want to focus so much on. So there is an issue about the normalization here, but it's maybe not the most central one for us right now. But otherwise, yes, fixing a normalization, this thing is uniquely defined by what is written. And no surprise, one of the main players in the game are so-called degenerate chiral vertex operators. So this is just the special case here now where this M is -1/2 and P2 and P1 differ by a shift by plus or minus 1/2. So in this special case, something remarkable happens. So I will abbreviate this guy as just psi s of, well, actually for this guy, I prefer to use the argument y. We'll see in a moment why. So it is well known that this guy have a remarkable property, namely they satisfy a second order operator differential equation with respect to y dependence. Psi s of y, normal ordered, and this is just, so let me be completely explicit here, y smaller than, k smaller than -1, y to the minus k minus 2, l k to the left of the chiral vertex operator, plus then the remaining guys being to the right of the chiral vertex operator like follows. We first have psi s of y and then the lk. So that is the precise definition of the normal ordering, and then it is a well-known result going back to Belavin, Polyakov, Zamnochikov that this operator differential equation is satisfied for this chiral vertex operator. So what is then natural to consider is compositions of such chiral vertex operators. Here let's pick, it's not absolutely crucial to consider this one, but let's be specific and pick one. So what you should start observing at this stage is that some of the parameters that we have in the Riemann-Hilbert problem start appearing here like the m's, which are then associated to external punctures. Well, I should have said actually what I will do is by convention, but that's no restriction of generality, to move the point Zn to infinity. And then we can study compositions like this one, n minus 2, p n minus 3, p n minus 2, z n minus 2, and so on. You go on till you reach m2, p1, m1 of z2 acting, say, on m1. This would also correspond to z1 to setting to 0, which I can also do without loss of generality. So that's what we shall do. So that defines, acting with these vertex operators on some state, some highest weight state M1 produces another state, which I denote like that. All right, so, and then I...
State depends only on your P levels, or
What's it? It depends on what? Yeah, it depends on m's, which were our fixed external parameters, and I'm introducing a collection of p's. So there are some n-3 extra variables p, pr we're introducing here. So it is half the dimension of the space, and that's of course going to be important to keep track of the parameters here. So y s prime s is now a function depending on m. That's the collection of all m's p, collection of all p's z. These are the collection of all z's, a y0 and a y. So this is just defined as the matrix element mn. Then we're inserting two degenerate guys, psi s prime of y0, psi s of y. And then we're taking the overlap with this state, which represents sort of the background in which we're computing expectation values. And now another well-known consequence of this operator differential equation is that this then is going to satisfy a partial differential equation. Satisfies bpz acting on y equals to 0, where this differential operator dbpz, bpz, beloved Polyakov-Solomochikov, is in our case the delta minus 1/2 over y minus y0 squared plus 1 over y minus y0. Well, it probably doesn't matter so much now for us, but let me write it anyway. Plus r equals to 1 to n minus 1 delta r y minus zr squared plus 1 over y minus zr d by dzr. All right, let me lift it to get better visible. How am I doing with time, by the way? Thanks. Okay, so here comes the main result. Let me formulate it. So the main definition now, I have to do something, is to define S prime a dual state by doing a sort of Fourier transformation. Z to the, we're taking vectors of integers in Z to the n minus 3, a product of exponentials e to the I nr tau r, and then we're taking the theta s prime s. Well, I was previously suppressing all the dependencies, but it was in particular depending so here I'm, say, reintroducing the dependence on the p variables, and that's the argument here, like that. Again, Nikita may already recognize this kind of thing because he has done something similar in the case of instanton partition functions. But okay, let's see why and how it connects.
Is this like a dual partition?
Yes, that's why D is being used here. It is the dual conformal block, and sort of what I'm hinting at is that this is probably...
I think I can steal your punchline.
Huh?
I think I can steal your punchline.
Yeah. Well, anyway, okay, so anyway, I can sort of... Forgive me. So, and the y is, of course, then with some convenient prefactor to kill the singularity in y minus y0. We're just taking now the overlap of the degenerate fields psi s prime of y0, psi s of y with this dual state. So these are main definitions. And now we have two main statements. So one is y dual s prime s. Now y, just consider as function of y, is solution of the Riemann-Hilbert problem. And corollary is that if we're considering now the thing without these degenerate fields inserted, sigma tau of z, which is mn theta of s comma minus s, is, well, maybe I'm trying to use different chalk, the isomonodromic, tau function. So that's the statement of the main results. So the plan for the rest of the talk is, well, first to discuss a few, well, first to say what I mean by this. I mean isomonodromic tau function and so on. That's what may not be familiar to all of you. Next, to make a few remarks on implications, and in the end, try to explain the key observations in the proof, which is actually, well, once you have understood a little bit of the background on conformal field theory, especially related to the degenerate fields, it's in the end amazingly simple. And there's just one little twist, one little remarkable observation one has to make about a peculiarity about c equals 1.
Do you know a four-dimensional gauge theory explanation of this result?
No, I mean that's probably what it.
It's just one line.
Very good. Yeah, I was hoping for that sort of you could tell the other side of the coin. I mean, this is one side, CFT side, and good. So yes, to explain about tau function. So what is isomonodromic deformations and how is it basically coming for free now from a solution to the Riemann-Hilbert problem? So let's consider a matrix of functions again, which is really, well, I'm mostly suppressing most dependencies, but those that matter are exhibited here. So this is dy of the capital Y times y to the minus 1. And it is easy to see from, well,
how much is the difference with
well, they were using fermions. We don't have any fermions yet. And I think the punchline is that there is a sort of new version of bosonization, fermionization at work here, which I think is quite interesting because some things which are simple in one picture, the fermionic picture of Sato Jimbo-Miwa, they're complicated here and vice versa. So for example, yeah, so it's a new way of representing it, which simplifies some things, I believe. And maybe it becomes clear also a little later. Oh, it has disappeared. Well, anyway, it is easy to see that this matrix must have this form, so it can be written as a sum of simple poles with matrix-valued residues, which of course don't depend on the y, but do depend on the z's. And the whole fun part is to understand dependence on z's. And what follows very easily from the CFT, I mean, if you know a little bit about CFT, then you know that monodromies of conformal blocks are represented by constant matrices independent on the moduli or the parameters of the underlying Riemann surface. And this is all I need to use to conclude that if I vary the z's, then this guy must change in such a way that the monodromy of the connection defined thereby, connection say nabla dy plus a of y, stays constant. So this means these guys, must deform in an isomonodromic way. So let me write it here. ZR to ZR plus delta ZR leaves MK, well, no, monodromies. It's not yet the MKs, that's the point. It's really the whole point to understand the relation between this and the monodromies. Well, no, okay, let me be, sorry, here I was probably saying confusing. So the claim is this thing here, which depends on the parameters sigma and tau we have used to parameterize our matrices MK with, solves the Riemann-Hilbert problem, namely it has monodromies exactly given by these matrices. That's the claim. And indeed, therefore, I could have put here MK. Sorry, this was confusing. Yeah, and then it's a classical result, going back to Schlesinger, that this is equivalent to a system of partial differential equations, nonlinear in these parameters or in the unknowns A, these matrix valued residues, ZR minus ZS, and d by d ZS of AS is something very similar, minus a sum S R not equals to S, again commutator AR AS, ZR minus ZS. All right, so this is saying having Riemann-Hilbert problem from CFT produces you automatically solutions to Schlesinger's equations. That is well known and not new. And to explain what tau function is, let me note that there's a Hamiltonian formulation for these equations obtained by defining Hamiltonians, HR minus some trace AR AS over ZR ZS, sum over S not equals to R. And there's a Poisson bracket. Well, let me skip it here for reasons of time, which is well known and I could write. And then, so with this Poisson bracket that I skipped and these Hamiltonians, this is Hamiltonian. And tau function is defined as generating function of Hamiltonians, namely d by dZr log tau is minus HR. So, yeah, let me mainly note here that the corollary that the tau function defined as such equals to this correlator in the CFT. This is an easy consequence and also relatively well known of the conformal word identities in the equals 1 CFT we're discussing. So, so maybe let me put it here. This is conformal word identities. All right, how much of time do I have left to gauge my
7 minutes.
7 minutes? Well, that's not ideal, but let me try. Okay, good. Yeah, let's see what I shall try to say. So 4 was about some implications. What I wanted to say is there's a relatively simple way to understand, well, I mean, to get the relation to the Fermionic picture, we simply have to add a U1 factor, some free boson phi 0, And then by multiplying our degenerate fields with these U1 factors, so e to the I, or what was it? Yeah, simply that. So that is the capital psi, that is the lowercase psi. And similarly for psi bar with just here a sign change and here a sign change. And these are really free fermions. Separately, they would not be fermions like that. So these are free fermions, and therefore, indeed, basically what we've proven is a kind of Bosonization formula of the Sato-Jimbo-Miwa results, where they have represented these guys in terms of certain Fermi bilinears. Okay, so now there's alternative representation in terms of bosons. And yeah, the other remark here I wanted to make is that I think that this should be some ingredient for understanding how Nikita likes to call BPS CFT correspondence is related to AGT correspondence, because that is what AGT tells us represents the, the Y's without D is what, according to AGT, represents the unrefined instanton partition functions at epsilon 1 equals minus epsilon 2. And now the claim is just doing the simple Fourier transformation produces dual objects which are Fermi correlators, and therefore, as you already said, they should have a direct, there should be a direct way to understand from the gauge theory why.
So this, as a monodromic null function, correspond to epsilon 2 equals to 0, right? It's like it's C equals infinity.
No, but okay, here, I'm talking about C equals to 1, and indeed that's.
The claim is that
yeah.
C equals 1,
yeah.
there is some, so
yeah.
dualized, it becomes C equals infinity.
Right, but the Fermionic representations, at least in the literature that I know of, therefore C equals 1, right? So this is the remark I wanted to make here, that these Fermionic representations now getting generalized by this Fermionization or Bosonization story. So, okay, so let's brief about that, but I really want to give you some idea about the proof, because really somehow the key observation is quite nice and simple. Okay, so I have been mentioning that our correlators satisfy, with respect to y, some differential equations, some partial differential equations of Belavin-Polyakov-Zamolodchikov. And from this equation, you can derive some algorithm. Wow, what am I doing? Algorithm for computing monodromies. And, well, at the end of the day, you can massage it into basically the same form as before. That's why we presented it in this way. Namely, we break up our monodromies into a sequence of arcs. We assign matrices to each of the arcs. And in fact, I can keep almost all these matrices, because here we have the parameters sigma, which are just the same parameter sigma as we had before, etc. Except that, of course, in the CFT, before doing this Fourier transformation, we don't have any parameters tau. So the interesting thing is just how the tau arises in this Fourier transformation and how it comes about. So here, we would be getting operator-valued matrices now, which act on spaces of conformal blocks, where these T R hat, say, S prime S, would be delta S prime S, e to the, and then some operator T, how did I want to call it? Simply TR to the power S. So that may be plus or minus 1. The rest is really unchanged. I should introduce this guy. So this guy, what is it? So it acts, here to begin with, we're talking about the y's, not y duals. And then focusing again on the relevant dependencies with m's and so on. This is just shift operator for p's. So it would shift So this is a vector formed out of the p's, and we're shifting on the rth position then by 1/2. Well, actually, I think minus 1/2 in some conventions. Okay, so this is just finite difference operator, which shifts by a finite, in this case, real amount.
So first, when you wrote down these matrices, the only thing you need to check is that you can construct by gluing from them the matrices M,
Yes.
which are what condition on M?
No, I mean, this is, I mean, okay, the monodromies are always just changes between different bases in the space of conformal blocks. Now, I'm claiming here that in this case, if I focus on just the monodromies of a single degenerate field, then this can be represented basically as operator-valued matrices which do not preserve the same conformal block, but they're in general transforming a given conformal block into a different one. But the shift is, the difference is relatively small. It is just, it shifts the arguments p in general. So
originally, this middle line, yeah,
Yeah.
So, there were no conformal blocks, yeah?
Yes.
Just from these formulas, you were checking that taking all products, you get matrices M, which are something like which satisfy the condition of product to unity and all other initial axioms. Yeah? Now you say that when you deal with this particular conformal blocks, you only change t's, replace them by the operator, which take into account this shift of p induced by degenerate field, right?
yeah, so let me make this statement a little more precise. The analytic continuation of these conformal block y along curve gamma can be represented as sum over conformal blocks y, where I'm summing over, of course, here these matrix indices, but I also have to sum over a certain collection of shifts here. So there's a collection of these functions y with a finite number of shifts which will appear as a consequence of this analytic continuation. So this is why a priori the problem that you get from CFT is more complicated, and it is not a priori not immediately obvious why this should give you solution to a Riemann-Hilbert problem. It's a rather different story a priori. We're getting linear combination of basis elements of a basis for the space of conformal blocks, which is not just given by a 2x2 matrix, but also it has some shifts here. Okay, is this clear?
Well, I can't say this for you.
What is not clear?
No, I'm just, well, it's clear what you are doing here, and it's clear ideologically what's the origin, but, so you say that, just very strictly, so you're summing, when you make this transformation, you shift not a single p, but you have somehow to sum over the shifts of all m minus 3.
In general, yes. It depends on.
But by this particular quantity corresponding to the general field, yeah?
That's right. You see, but it's easy to see, say, from the pictures which p's you have to shift, right? It is always the p's associated to the annuli that you're crossing on the way. If you're not crossing a certain annulus to produce the monodromy around a certain boundary component, you don't have to shift the p. If you cross it, it's going to be shifted. Yeah. So that is observation number one. Number one, we have an algorithm for computing the monodromies in this sense as some operators acting on the space of conformal blocks. And now, second key observation is that the resulting operator-valued matrices are rational functions of only two variables, namely UR is exponentials of the PRs, 2 pi PRs, and VR is TR squared. Why TR squared? Well, you're getting a shift when you cross these annulus, but say you see immediately to return to the base point, you have to cross it another time, and this amounts to the fact that in the resulting monodromy matrices, these matrices always act by conjugation, so they're like a twist, and therefore you're always getting this shift here squared. And similarly, you have to argue for this that, yeah, but now, and this is the peculiarity, I mean, in general, say for general C, these are, of course, non-commuting guys, so they're satisfying some Weyl algebra. And here, I mean, in general, there would be some Q squared. And here, it is 1 for C equals to 1, VSUR. So the Weyl algebra, which represents these quantized, well, these quantum monodromies, becomes classical. Therefore, you can simultaneously diagonalize UR and VR, and this Fourier transformation, which is still on the blackboard, is just what does the job. So you're diagonalizing, so that's the last remark I want to make. So this Fourier transformation, so this formula here, let me call it FT for Fourier transformation. What it does is just, it diagonalizes VR with the eigenvalue e to the I tau r, and therefore it produces the passage from these quantum objects, these operators containing shifts, to something classical, which are really the classical monodromy matrices we wanted to have. Okay, I shall stop. That's it. Thanks.
Questions?
Yes.
The question how to compute this whole function from CFT. We need to know the structure constants for this theory. And if we look at the answer of this company, we see that these structure constants are highly non-symmetric with respect to the three arguments. And what is the CFT explanation of this fact?
Well, okay, thanks. That's a very good question. So that is part of what I mentioned but suppressed, namely it is the story of the normalization of the Vertex operators. So what okay, so let me spend a few words on that. So what I'm assuming here, and this is similar basically in the story of Oleg Lissovy and Nikolai Yorgov. So that this matrix element is given by a non-trivial function n of P2 m P1. This is, if you wish, structure constant, or if you would consider non-chiral context, then you would require that absolute value of this, I mean, then the absolute value of this would be related to a three-point function or something like that. But okay, here it's a normalization factor. How does it affect the story? What is heavily dependent on the choice of these normalization factors is this matrix in particular. However, there is a certain amount of freedom in the choice of these normalization factors, which would correspond to redefinitions of these coordinates sigma and tau. Namely, you can shift the taus yet once more by functions of sigma. So these are not, say, God-given coordinates. You can use different ones which are equally good. So changing this normalization would change the definition of the tau variables. So there's a freedom. But of course, there's sort of some choices better than others. And here, in fact, this choice does differ from the one in the paper on the penalty V6. But it is more convenient because, in fact, it gives a somewhat more symmetric result for these matrices and so on. So, but yes, it does play some role, and it does play some role for getting these simple cosines and so on. If I had put 1 here, then, for example, this would be gamma functions, and it would be extremely hard to guess such a result. So it is quite crucial that we're using the simplifications coming from a clever choice of these normalization factors. And then for the question how to compute like tau functions, well, I think this is one of the advantages of this bosonic representation. Namely, these, for example, there are famous results of Jimbo from '82 about asymptotic expansion of tau function, which are now basically trivial corollaries of this bosonic representation. Namely, you're just getting it from the standard BPC-like factorization of conformal blocks. You read off, say, processing the definitions, these Jimbo's result. So this concerning computation, and or for example, you can use all the nice results on instanton counting to compute the coefficients to any orders in the expansion in powers of Q. So all this computational power that you have from CFT or the added value from instanton calculus, you can now use, for example, to improve a lot on these results of Jimbo and company.
Any more questions?
So what is the gauge theory explanation?
It's a blow-up formula.
The blow-up formula? Good, yeah, okay, I'm curious to learn.
Let's thank your